Good morning. Many mathematical statements assert that a property is true for all positive integers. Examples of such statements are that for every positive integer n factorial is less than or equal to n to the power n cubed minus n is divisible by 3. A set with n elements has 2 to the n subsets, and the sum of the first n positive integers is equal to n times n plus 1 over 2. A major goal of this chapter and the book is to give the student an understanding of mathematical induction. Mathematical induction can be used to prove statements that assert P of n is true for all positive integers n, where P of n is a propositional function. A proof by mathematical induction has two parts: a basis step where we show P of 1 is true, and an inductive step where we show that for all positive integers k, if P of k is true, then P of k plus 1 is true. So when you make your proofs by induction, I want you to label the basis step and label the inductive step. Mathematical induction. The principle of mathematical induction: to prove P of n is true for all positive integers n, where P of n is a propositional function, we complete two steps: the basis step, where we verify that P of 1 is true, and an inductive step, where we show that the conditional statement P of k implies P of k plus 1 is true for all positive integers k. Expressed as a rule of inference, this proof technique can be stated as P of 1, and for all k, P of k implies P of k plus 1 implies for all n, P of n. In proof by mathematical induction, it is not assumed that P of k is true for all positive integers. It is only shown that if it is assumed that P of k is true, then P of k plus 1 is also true. Thus, a proof by mathematical induction is not a case of begging the question or circular reasoning. Example 1. Show that if n is a positive integer, then 1 plus 2 plus ... plus n, or the first n positive integers, is equal to n times n plus 1 over 2. Basis step. P of 1 is true because 1 is equal to 1 times 1 plus 1 over 2. Inductive step. For the inductive step, we assume that P of k holds for an arbitrary positive integer in k. That is, we assume that 1 plus 2 plus ... plus k, the first k positive integers, is equal to k times k plus 1 over 2. Now we must prove that 1 plus 2 plus k plus 1 is equal to k plus 1 over k plus 1 times k plus 2 over 2. So we apply the inductive hypothesis to the left side, and we take the first k integers and we replace it with our sum, k times k plus 1 over 2, and we have k plus 1 for the k plus 1 integers. Then we algebraically transform our result until it matches the right-hand side. I want you to note what we did in the inductive step. In the inductive step, we stated what we must prove, and we applied the inductive hypothesis to the left-hand side. We never operated on, we never put any algebraic operations on the right-hand side. So you have to stay on the left-hand side, and you always have to apply the inductive hypothesis, and you always must state what it is that you are to prove. Example 2. Find a formula for the sum of positive odd integers. Then prove your formula is correct using mathematical induction. After some fussing, we find that the sum from I equal 1 to n of 2i minus 1 is equal to n squared. Please refer to the table below. For integer 1, the sum is 1 and the result is 1. For the integer 2, it's 1 plus 3 is equal to 4. For the integer 3, it's 1 plus 3 plus 5 is equal to 9. For 4, it's 1 plus 3 plus 5 plus 7 is equal to 16. For n, it's the sum from I equal 1 to n of 2n minus 1 is equal to n squared. Basis step. P of 1 is true because 1 is equal to 2 times 1 minus 1 is equal to 1. Inductive step. For the inductive hypothesis, we assume that P of k holds for an arbitrary positive integer k. That is, we assume that 1 plus 3 plus dot 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 plus 2k minus 1 is equal to k squared. Now we must prove that 1 plus 3 plus dot 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 plus 2k minus 1 plus 2 times the quantity k plus 1 minus 1 is equal to k plus 1 squared. Apply the inductive hypothesis to the first k items, arriving at k squared, and the whole equation becomes, or expression becomes, k squared plus 2 times the quantity k plus 1 minus 1. Algebraically transform our result until it matches the right-hand side, and we arrive quite easily at the quantity k plus 1 squared. Example 3. Use mathematical induction to show that 1 plus 2 squared plus dot 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 2 to the n is equal to 2 to the n plus 1 minus 1. Let P of n be the proposition that the sum of the geometric series 1 plus 2 squared plus dot 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 plus 2 to the n is equal to 2 to the n plus 1 minus 1 for the integer n, basis step. In this time, we're using P of 0 rather than P of 1, which is also permitted. P of 0 is true because 2 to the 0 power is equal to 2 to the 1 power minus 1, which is equal to 1. The inductive step. For the inductive hypothesis, we assume that P of k holds for an arbitrary positive integer k. That is, we assume that 1 plus 2 squared plus dot 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 plus 2 to the k is equal to 2 to the k plus 1 minus 1. Now we must prove that 1 plus 2 to the 2 power plus dot 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 plus 2 to the k plus 2 to the k plus 1 is equal to 2 to the k plus 2 minus 1. So we apply the inductive hypothesis to the left side, arriving at 2 to the k plus 1 minus 1 plus 2 to the k plus 1. Algebraically transform a result until it matches the right side. 2 times 2 to the k plus 1 minus 1 is equal to 2 to the k plus 1, which is equal to the 2 to the k plus 2 minus 1, which is what we want.